Hi students, in this video we're going to cover vectors and three dimensions. We will learn how to do some basic things in GeoGebra, so follow the link in the description to geogebra.com.org, /3D, and you can follow along. So initially we're going to talk about defining R3. So R3 is the three-dimensional space where we have three base axes. Generally, we're going to call this the x-axis as one horizontal axis, the y-axis as the vertical axis, and the z-axis as the axis that rises out of the plane. We can see this in GeoGebra. So again, navigate to geogebra.org/3D. So the red axis is our the side with the arrow is the positive x-axis. The green arrow, the green axis, the positive side is the one with the arrow. That's the positive y-axis. And the positive z-axis comes out of the xy plane. So you can see that we have four divisions above the x-axis, the xy plane, and four divisions below the xy plane. These are called octants. We have 8 octants because when you intersect three things, we can get 8 different regions. Our work is generally going to be in the first octant. Sometimes we'll extend to all of the octants that are above the xy plane. So the first thing that we're going to do is plot 4 points, one in each octant. And we're going to take the point 1, 2, 4. So 1, 2, comma 4. So that point is, all right, so if we look at the x is 1, the y is 2, then if we turn it this way, we see z is 4. So it's out here in space. And so now we're going to apply 3 other points, one in the other 3 octants. So then we could have the point 1, -2, 4. Now we want our z to be positive. I think in the notes I put, let's see what I say. I said apply 4 points in GeoGebra, one in each octant above the xy plane. So we have one, and we'll call this the second octant if we want to. Well, yeah, I guess we can say the fourth octant. I don't know. It doesn't really matter. So then we have -1, -2, and +4. And that's going to give us a point in a third octant where, again, the z is positive. And the last one, obviously, we could make the x negative, the y positive, and the z stay positive, and we get a fourth point. So we have 4 points and 4 octants, and this is how points look in three-dimensional space. We won't do a lot of this drawing on paper because we can't draw in 3D and 2D, but we can try to visualize this in three-dimensional space using some technology. All right, so we're going to talk about planes in greater depth in chapter 12. Right now, we want to talk about having planes that are parallel to the coordinate planes. The 3 coordinate planes that we have are the xy plane, which means that z is 0, the xz plane, which means that y is 0, and the yz plane, which means that x is 0. So one thing that we want to do is we want to find a plane that's parallel to the xz plane that contains the point A. So the xz plane means that y equals 0. So y equals 0 is this plane. This is the xz plane. Y is 0, and then x and z can be whatever they want. That's just like having another two-dimensional coordinate plane. It's just not the xy plane. So now, if our plane, the plane that's parallel to this teal plane is going to contain the point A, it means that the y coordinate has to be 2. And x and z can still be anything they want. So when we type y equals 2, we get a second plane. And let's change this color. Let's change this to, I don't know, let's go with purple. Oh, so all right. So we made the xz. So we made the xz plane purple, it doesn't matter. So now the plane is parallel to that contains point A is the y equals 2 plane. So this is a plane that's parallel to the coordinate plane, the xz plane that contains the point 1, 2, 4. You see if you can make the other two planes that are parallel to the xy plane and the yz plane that still contain this point. So, all right, if we're finding the plane that's parallel to the xy plane, that means that z equals 0. We're going to get another, I don't know why they don't do new colors. So let's change this color to, I don't know, red. And so we get, and we'll turn some of these off so stuff doesn't go crazy. All right, so now we have, so our XY plane is here. And to contain the point 1, 2, 4, the Z value has to be fixed because Z needs to go through 4 and it needs to be parallel to the XY plane. So when we type the plane Z equals 4, I don't know why I keep spinning. So we now get this plane that's parallel to the XY plane that contains the point 1, 2, 4. And in a similar fashion, if we wanted to contain the point 1, 2, 4, but be perpendicular to the YZ plane, the YZ plane is going to be x equals 0. So we'll just change this to be x equals 0 instead, press enter. And so now when x is 0, y and z can be whatever they want. And we still want to find a plane that contains that point 1, 2, 4, which means that x equals 1 needs to be the other plane. So we had x equals 1, well, y equals 2, and the other one was z equals 4. And we'll change the colors of all of these to something different. Settings, let's go to color. Let's make that one bright green. Let's make this one dark blue. Z equals 4. Let's make that white's a crazy color, but let's go with that. And x equals 1. Let's go with, I don't know, pink. Let's go with orange. Why does this do P of Z? We wanted Z equals, maybe that fixes everything. We have our point 1, 2, 4. So you can see that we have, no, P of Z equals, take that out. We have x equal, y equals 2, x equals 1, z equals 4. Yeah, we have our, so you can see we have 3 planes that go through those points, and they're all pairwise perpendicular. We can say, we can pick 2 and they can be perpendicular to each other. So those are the 3 planes that are parallel to the coordinate planes that contain that point. That is something that you will be expected to reproduce. So moving on. All right, so in 3D, what we're really going to focus on is vectors. And just like we have in 2 dimensions, a vector that has 2 points, the tail of the vector is one of the points and the head is the other point. The direction depends on the way our arrow is drawn. So if we have the vector PQ, that means that the tail starts at P and the head is at point Q. And so the magnitude of that vector we can find by doing the distance formula. Let's clear out, let's refresh GeoGebra and see how this vector looks. All right, so to draw a vector in GeoGebra, we type the word vector and we press enter. Whoa, nope, we don't press enter. We type vector. I was trying to get to the shortcut. All right, so the start point is where we want to begin, and that's going to be at, we're going to say 183. So we're going to start at the point, actually we said PQ, right? So 905. So we're going to have the point 9, 0, 5, close parenthesis. Well, I'm pretty sure we need to put another set of parentheses around that. Open that. No. GeoGebra is difficult at times. Give me a moment, kids. All right, so let's open this up. So now we have the point 9, 0, 5. Close out those parentheses. So that's our start point. And you can see right now it's going to draw us a vector from the origin and goes out to the point 905. Now we want to change this so that we actually have 2 points. And the other point was, I believe, 1, 8, 3. And close parentheses and press enter. -8. So we might have to zoom out a bit. Did this not? I can't. Oh, did I turn it off? There we go. All right, so now we get this vector in space. Did I type the right coordinates? 1, 8, 3. Yep. All right, so let's put in our 2 points. So we have 9, 0, 5. That's our point P. And then we have, excuse me, the other point is 1, 8, 3. And so we see we get a vector that starts at point A and goes to point B. Starts at 183, goes to 905. So in three-dimensional space, the magnitude of this vector is no different than if it was projected onto the XY plane and we found the length that way. It still is a two-dimensional quantity when we're talking about distance. It just exists, the vector exists in 3 dimensions. So when we're finding the magnitude of that vector, we are just doing the magnitude of, so the magnitude of vector PQ is going to equal the square root of, so we'll say 1 minus 9 squared plus 8 minus 0 squared plus 3 minus 5 squared. And that's going to give us 1 minus 9 is 8, well, negative 8. Negative 8 squared is 64. So the square root of 64 plus 8 squared is another 64. It's 128. 3 minus 5 is negative 2. Negative 2 squared is 4. So 128 plus 4 is the square root of 132. That is equal to the square root of 4 times the square root of 33. So that is 2 square root 33. So that's the magnitude of that vector. That's one thing we can do in three-dimensional space. All right. So moving on, a sphere is it's the set of points in a three-dimensional space that are a fixed distance from a point that we're going to call the center. It has a similar equation to that of a circle, except we add on the third dimension, the z dimension. Excuse me again. So the formula is, again, just like a circle, we just add a third dimension. So for our guided example, we want to find the equation of the sphere centered at 213, and it contains the point 616. So first the equation, we're going to write, we're going to have x minus 2 squared plus y minus 1 squared plus z minus 3 squared equals the radius squared. And so now to find the r squared value, we can just substitute in the point that's on the sphere. So we're going to get 6 minus 2 squared plus 1 minus 1 squared plus 6 minus 3 squared, and that's going to equal r squared. So 6 minus 2 squared, that's 4 squared, that's going to be 16, plus 0 plus 9, and that's going to equal 25. So our r squared value is 25. So the equation of our sphere is x minus 2 squared plus y minus 1 squared plus z minus 3 squared equals 25. I don't know why I crossed. Let me just erase that. So let's go over to GeoGebra and type that in. And it's better to just refresh GeoGebra and get a new one. Kind of lags for me. So we had x minus, let's see if I can remember, x minus 2 squared plus y minus 1 squared plus z minus, I believe it was 3 squared, and that equaled 25. Cool. So now we get this circle, this sphere that has a radius of 25. So let's put in our center 2, 1, 3. And then we're going to plot the point that's on the sphere, 6, comma, 1, comma, 6. And we can see that that point is exactly on the sphere. And then if we put in the vector that contains the 2 points, do we have a shortcut? Nope. All right, so we're going to have to start out typing vector, and it might complete it for us. So vector, and so our start point is, all right, you know what? Here's a handy shortcut. We can do A, and then we go back over here, comma, and it should give us B. Yeah. All right, so that's a handy shortcut. Once we have the points A and B, we can just do the vector between the 2 points. So we can see that from the center to the edge of the sphere. And again, the sphere is the outer, it's the shell of the sphere, not the internal part. A ball is going to be if we have the shell and everything beneath it. So like the inside of the ball, like if you think about I don't know, like one of those squishy balls or something where it's solid all the way through. That's the internal part is the ball. The shell, the part that we can touch, the surface area, is the sphere. So, all right. So you try. So we have the equation of a sphere has a diameter that has those endpoints, and you have to find the equation. And maybe you can graph it in GeoGebra to like verify that you did it correctly. All right. So to get our center, we need to find the midpoint of the diameter. So we're going to say our center is, all right, so 3 plus 9 is 12, divided by 2 is 6. 1 plus 5 is 6, divided by 2 is 3. And 4 plus negative 2 is 2, divided by 2 is 1. So the center of that sphere is 6, 3, 1. The equation that we're going to have is x minus 6 squared plus y minus 3 squared plus z minus 1 squared equals r squared. Now, if we want to find the distance from if we want to find our r squared value, we could find the length of the diameter divided by 2, or we could just substitute in either point and it's going to give us r squared. So let's do that. So we're going to have 3 minus 6, which is negative 3 squared, so that's going to be 9, plus 1 minus 3 squared is, what's that, negative 2, so negative 2 squared is 4, and then 4 minus 1 squared, which is, 3, and 3 squared is 9, and that equals r squared. So we have 9, 4, 9. And that's going to be 9 plus 4, 13, plus 9 is 22. So our r squared value is 22. So we'll put 22 here. So let's see what that looks like. Let's refresh GeoGebra again. And we're going to have, I forgot already. Let's make it up. X minus 6 squared plus y. All right, let's not make it up. Y minus 3 squared, y minus 3 squared, nope, square goes on the outside. On the outside, why is this being difficult? Okay. Y minus 3 parentheses squared plus z minus 1 squared equals 22. So that is the equation of the sphere that we get. Cool. And you can plot the points if you want to. I'll leave it up to you. It contains that the diameter is going to be the segment that goes between those. Moving ahead. All right, so some properties of vectors in 3 dimensions, I'm sorry. So the component vector that we get, x1, y1, z1, is going to be the position vector where the tail is at the origin, and I'm sorry, what did I put? It corresponds to the position vector whose tail is the origin, yeah. And the head is the point x1, y1, and z1. If we had two component vectors like u and v, they add and subtract like you think they would. You add the, like if we were adding and subtracting the two vectors, you would add the first components, add or subtract the first components, add or subtract the second components, and add or subtract the third components. And then if I gave you like a scalar value like 4 and you multiplied it by the vector, that's really multiplying each component by 4. Just like we did in lesson 1 or 11.1, two vectors are parallel if they are scalar multiples of each other. So for some quick independent practice, you look at these 4 vectors and tell me which ones are parallel to each other. All right, so if you are following along, it seems as if A and D are parallel to each other because if you divide all of the components of vector A by -2, you get the vector for D. And B and C are parallel because if you multiply each of the components of vector B by -2.5, you get vector C. And A and B, since A and B aren't parallel, neither are C and D. So these are the two pairs of parallel vectors that we have. In R3, and we'll talk about this in great length in linear algebra, we have 3 unit vectors. We can think about these as being our basis vectors if we're talking about linear algebra. You have the I vector, which we typically associate with X, the J vector that we associate with Y, and the K vector that we associate with Z. For I, X is 1, Y and Z is 0. For J, X and Z is 0, Y is 1. And for K, X and Y is 0, and Z is 1. So if we were expressing the component vector 5, 3, 7 in terms of unit vectors, it's going to be 5 times vector I plus 3 times vector J plus 7 times vector K. And this is the notation that we have for that. It's very straightforward. We're going to see these, we're going to see vectors written both ways. Sometimes we'll see it like I've underlined. Sometimes we will see it in terms of the unit vectors. So now another thing is like we have 3 unit vectors, the 3 basis unit vectors for R3, but we can make a unit vector from any vector. Like when we talk about linear algebra, that's going to be like having a linear transformation. We do like a change of basis. But right now, just know that if we have a vector, if you divide that vector by its magnitude, you created a unit vector and a unit vector has a key property that its magnitude is 1. So for our guided example, we want to find 2 unit vectors that are parallel to the vector PQ. So first, we have to determine vector PQ. So vector PQ is, so let's see, PQ is equal to 1 minus -2. Oh, I'm sorry, let's put this in vector notation. So pointy brackets. 1 minus -2, comma, -1 minus 3, comma, 1 minus 1. And that's going to be 3, -4, 0. Cool. So we want to find 2 unit vectors parallel to PQ. So to get a unit vector, we need to find the magnitude of PQ. So the magnitude of PQ is equal to the square root of 3 squared plus -4 squared plus 0 squared, which is the square root of 25, which is 5. So the magnitude of PQ is 5. So one vector that's parallel to this is 2 unit vectors. So one is you just divide PQ. So PQ divided by the magnitude of PQ is going to be, that's effectively having 1/5 times 3, -4, 0, which produces one vector that is 3/5, -4/5, and 0. The other vector that we could have is negative vector PQ, I'm sorry, I should put the arrow. So negative PQ divided by the magnitude of PQ. So that's going to be negative 1/5 times 3, negative 4, and 0. So instead, we get negative 3/5, positive 4/5, and 0. Cool, cool, cool. All right, so now for part B, we have to find two vectors of length 8 that are parallel to PQ. So these are unit vectors already. They have a length of 1 or a magnitude of 1. So to find vectors that have a magnitude of 8, we can just multiply each of these unit vectors by 8. So we'll end up with one vector is, we'll just do plus and minus. So plus and minus 24 over 5, negative 30. So plus and minus negative 32 over 5, and 8 times 0 is going to be 0 regardless. So those are two unit vectors that are, I'm sorry, those are two vectors that are length 8 that are parallel to PQ. All right, kids, that is our lesson on R3. It's just the foundation or the fundamentals. We will do plenty of application using physics and working all sorts of problems in class. Again, just the foundation. All right, see you all in class.